elastic stress analysis. We model our equipment based on the stress strain diagram, Hooke's law. If I apply the loading, there will be stress and also strain depending upon the modulus of elasticity which we have provided in the material as an input. There is a fixed modulus of elasticity value which has been given. And based on that, whatever loads we are giving, there will be stresses and strain related to that. Now, if that is the model, if I keep on increasing my pressure, it will keep on giving me the stress and strain. We don't provide the allowable or yield or tensile value of the material. Do you think it will give you the failure? Answer is no, it will not give you the failure. It will just give you the stress and strain. Okay. Then how to qualify that? How to say whether my material has passed or failed this analysis? On which basis we can make that statement? For that purpose, we have to classify the loads into primary, secondary, and peak. Peak when fatigue is there, otherwise you don't need. So primary, among primary also, you'll be classifying it as primary, general primary membrane or a primary bending. Okay. Or local primary, because primary is limited with allowable value. We cannot take it more than the allowable. If we try to understand that with a simple logic, that what exactly this type of analysis is, okay, what is elastic stress analysis? Consider it as a spring. Now, if I keep on applying the load, it will just stretch. Okay. I'm not taking it beyond some limit, but just consider when it is able to perform as a spring. Okay. So if I keep on applying the load, it will just elongate. It will show the deflection. Same way, your model, the pressure vessel model, if I just simulate in the similar manner, if you keep on stretching it, if you also see this as a, try to imagine a simple tensile bar instead of the spring. Okay. What will be the kind of stresses in that? If my vessel is not a complicated shape, it is just a round bar. And if I apply a load on that, what kind of stresses will be there? Axial tensile. Now, if you think in terms of primary membrane, primary bending, local, secondary, tensile is the nature. What is the classification of that stress, which will be there in the round bar? It's primary membrane stress. What is the limit for primary membrane? It's the allowable of that particular code. If I'm using a round bar in the tension, it is a very simple analysis. But will my pressure vessel also behave in the same way? Will this pressure vessel, if I'm just trying to pull it from both the ends, very similar to like we do for the round bars, do you think it will be behaving in the same way? The answer is no. It's a complicated shape, isn't it? So majority of the location in the longitudinal direction, you'll be having the primary membrane. No doubt about that. But the local points where you have a nozzle, where you have a flange where your vessel is getting connected, your shell is getting connected, all the discontinuity point, depending upon the shape, you may have primary bending or you may have local. If there is a thermal loading also, then you may have secondary. Okay. So if I want to qualify elastic stress analysis, the first thing after pre-processing, when we say pre-processing, it is the making the model, creating meshing and doing the analysis. Okay. So in the pre-processing and processing stage, your work is simple. You don't have to be very much expert of FEA tool. Okay. You can do the analysis, but that post-processing part where we classify these loads as a primary membrane, primary bending, local, secondary, there you need the expertise. If you are going wrong there, your complete analysis will be wrong. So post-processing is very important for these kind of analysis. Okay. Now, if you try to relate the primary membrane, we limit with allowable. What is the limit for bending type of stresses? Primary bending. PB is limited to what value? 1.5 S or to the yield point. Now you'll think that yield. If I'm taking the PB to the yield point, don't you think there will be failure happening at that point? If I'm taking the stress level to the yield level, why not the component is failing? How I can allow up to the yield? I'm not having any margin. If I'm allowing up to allowable, I'm having a margin. Okay. But in PB, for bending type of stresses, I'm taking the stresses up to the yield point. How it is possible? If I ask the total stresses across this cross section, what will be your response? In bending, you have tensile one side. Okay, and then stresses keep on reducing. At the center point, you will not be having any stress. Then below the center, you will be having the stresses in the opposite direction. So if I take overall stresses, what is the value? It will come out 0. Okay, and that is the reason you don't bother unless it is reaching the extreme point. If it is reaching to the yield limit, now if I go beyond, then it may start propagating from the extreme point where the stresses has reached to yield. Now, similar way, the secondary stresses are self-limiting in nature. It will reduce the stresses by deformation. Once it is deformed, the stresses will come down. And because of the self-limiting in nature, secondary stresses are allowed up to twice of the yield value. 3 times of our allowable stress value, which is twice of the yield. So we can go up to that point. That is why we classify the different types of stresses so that we can compare with the allowable given to those kind of stresses. That will be the post-processing work. When we say post-processing, you have the result from the software. Now you are trying to analyze and qualify those stress values. That is called post-processing, the report making part. In the elastic stress analysis, the pre-processing knowledge, like creating the model in analysis, adding the properties of the material, okay, doing the meshing, then finally applying the boundary condition and applying the loading. That is called pre-processing, and processing means you just run it in the software. That portion is not very critical and can be done comparatively way, but the post-processing is where you have to put lots of mind to analyze. Okay. So now you have to do the stress classification. You will draw SCLs, lines, which point it is primary membrane, where it is primary bending, where it is secondary, where it is local stresses, and then comparing that with the allowable. Okay. So that is the post-processing work. The knowledge required in that is little bit higher. You have to put mind. Okay. So that
Learning
is
static equipment design can feel overwhelming. ASME codes, UG clauses, thickness calculations, WRC checks, wind and seismic loads, and then PVElite modeling. If you're struggling to connect theory with practical design, you're not alone. Here's the structured solution. Introducing Master Static Equipment Design with PVElite, a complete industry-focused program covering pressure vessel design as per ASME Section 8, Division 1, heat exchanger design as per THEMA, support design, wind and seismic analysis, and complete PVElite modeling with practical examples. By the end of this program, you will be able to confidently design pressure vessels as per ASME codes, perform accurate shell and head thickness calculations, design and verify nozzle reinforcements, calculate wind and seismic loads for tall columns, design saddle, skirt, and bracket supports, and model complete vessels in PVElite, generating professional calculation reports ready for submission. This is practical, industry-ready capability. Along with structured technical training, you get access to a complete learning ecosystem. Over 100 hours of detailed video lectures, downloadable notes, and practice data sheets. Real project-based examples, access to a technical support community, and a course completion certificate validating your expertise. Hundreds of engineers have strengthened their design fundamentals through this program. Many are now independently designing pressure vessels and static equipment in real projects. This course has helped professionals move from theoretical understanding to practical execution. This is not just another course. This is a structured, industry-level training designed for working engineers. Our trainer is already trusted by a growing professional community on LinkedIn and YouTube, where thousands of engineers engage with technical content regularly. Click the link below and secure your enrollment today. Build the expertise that sets you apart.